Hi all. Today we'll be covering recursive binary splitting and pruning. Let's get started. Recursive binary splitting is the process used to create a regression tree. Picture the entire predictor space as one big region containing all of our training data. It is called binary because each step splits a region into exactly two subregions. Here, one split divides the space into two regions. And it is called recursive because the same process is applied again and again to each successive region, carving the space into smaller and smaller pieces. The approach can be summarized in 3 points. First, it is top-down. We begin with the entire predictor space and progressively split it into smaller and smaller regions. Second, it is greedy. At each step, we make the best possible split based on a criterion, such as minimizing the RSS. The algorithm does not look ahead to see whether a different split might lead to better results down the road. And third, we repeat. The same splitting process is applied recursively to each subregion. Let's walk through the steps of recursive binary splitting in greater detail. Step 1. Consider each predictor variable xj in the dataset, and for each xj, evaluate different potential cut points, s. For a given j and s, we partition the data into two regions. R1 contains the observations where xj is less than s, and R2 contains the observations where xj is greater than or equal to s. Step 2. Recall from the last video that the goal in building a regression tree is to select the regions that minimize the residual sum of squares, where yi is the actual response and y hat rj is the mean response in region rj. A binary split creates exactly two regions, so we apply that same formula with j equal to 2. The RSS for a candidate split is the sum of squared errors in region R1 plus the sum of squared errors in region R2. We compute this RSS for every predictor j and every cut point s, and identify the pair that results in the smallest value. That pair gives us the best predictor and the optimal cut point, and this search can be done quickly when the number of features is not too large. We then use the optimal j and s to split the dataset into the two regions. Step 3. Apply the same process recursively to each resulting region. We continue splitting until a stopping criterion is met, such as having no more than a fixed number of observations in each region, or reaching a maximum depth of the tree. Let's see how recursive binary splitting applies to the example from the last video. Recall our dataset with two features, x1 and x2. Each point also carries a response value y that we want to predict. Our job is to find the first split. First, consider x1 as the predictor variable, and evaluate the RSS from step 2 at every possible cut point s. Watch the RSS fall as the cut point approaches the best split, then rise again past it. Next, consider x2 and all of its possible cut points as well. Notice the RSS never drops as low as it did for x1. Using the RSS formula from step 2, we find that splitting at x1 equals 3.33 minimizes the RSS, bringing it down to about 112. So for any pair x1 and x2, we now have two regions, R1, where x1 is less than 3.33, and R2, where x1 is greater than or equal to 3.33. Next, we consider splitting region R1 further, but R1 already meets our stopping criterion, say fewer than 50 observations, so we leave it alone. We then consider splitting R2, again trying both x1 and x2 with all possible cut points, but now the RSS only involves the points inside R2. This time, we find that splitting at x2 equals 5.0 minimizes the RSS, bringing it down to about 16. Now we have three regions, R1, where x1 is less than 3.33, R2, where x1 is at least 3.33 and x2 is less than 5.0, and R3, where x1 is at least 3.33 and x2 is at least 5.0. No further splits are needed since all three regions now meet the stopping criterion of fewer than 50 observations. One final observation. When visualized in 2 dimensions, every split must be either a horizontal or a vertical line, just like the two splits we made here. One of the drawbacks of binary splitting is that it can lead to overfitting. Imagine we let binary splitting run unchecked on this dataset. As binary splitting progresses, each subset becomes smaller. Smaller subsets can lead to terminal nodes with very few data points. With fewer points in each subset, the tree can make splits that perfectly fit the peculiarities or noise within the training data. It might even create a branch for every unique data point. The result is a highly complex tree that classifies the training data perfectly, but performs poorly on new, unseen data. To address overfitting, a more effective approach is to first grow a large tree T0, for example via binary splitting, and then prune it back to obtain a smaller, more manageable subtree. Pruning involves removing some of the terminal nodes or leaves of the tree. This simplifies the model and helps improve its generalizability. By eliminating the less important nodes, the pruned subtree strikes a better balance between bias and variance. The primary goal of pruning is to select the subtree that minimizes the test error, which we could estimate through cross-validation or a separate validation set. However, directly evaluating every possible subtree is computationally infeasible because there are simply too many combinations. We'll see the practical solution shortly. To illustrate the difference between an unpruned and a pruned decision tree, let's look at an example. Here is the unpruned tree. It has been fully grown and contains all possible branches and leaves. Every path ends in one of 8 leaves. Now let's prune it. We cut off the branches below C1, C2, and C4, removing 6 of the leaves. The nodes C1, C2, and C4 no longer split, so they become the new leaves. The pruned tree keeps the essential structure of the original, but with fewer leaves and far less complexity. So how do we prune in practice? The answer is cost complexity pruning, also known as weakest link pruning. Step 1. Start by using recursive binary splitting to grow a full decision tree T0 on the training data. This initial tree should be large enough to capture all the potential splits and details in the data. Step 2. For each value of a tuning parameter alpha, there exists a subtree T of T0 that minimizes this quantity. The first term is the familiar sum of squared errors across all terminal nodes, and the second term is a penalty of alpha times the size of the tree. Here, the absolute value of T is the number of terminal nodes in the tree. Rm is the region corresponding to terminal node M, and y hat Rm is the predicted value in that region, typically the mean of the responses. Finally, alpha is a tuning parameter that controls the trade-off between the goodness of fit and the complexity of the tree. By varying alpha, we create a whole series of subtrees from the original tree T0. Higher values of alpha put more weight on the penalty term, which leads to more pruning and smaller trees. We now have a sequence of subtrees indexed by alpha, but which alpha should we pick? The answer is k-fold cross-validation. First, divide the training data into k equally sized folds. For each fold, grow a tree T0 on the remaining k-1 folds, and apply cost complexity pruning to generate subtrees for different alpha values. Then, for each alpha, calculate the mean squared error on the validation fold, and average those errors over the k folds to get the cross-validated error for each alpha. Finally, choose the alpha that minimizes the average MSE across the k folds. Go back to the sequence of subtrees and select the subtree corresponding to that alpha. This subtree is our pruned tree, balancing complexity and performance. Let's build some intuition for the role of alpha. Think of alpha as a dial that controls how aggressively we prune. When alpha is 0, the criterion reduces to the sum of squared errors alone. The tree stays fully grown as T0 with many leaves that potentially capture noise. This often leads to overfitting. When alpha is large, the penalty term dominates. Many branches get removed, and if alpha is very large, the tree may become too simple to capture important patterns, leading to underfitting. The goal is an intermediate alpha that balances the error against the complexity penalty. That balanced alpha, chosen by minimizing the average cross-validated MSE, yields a tree that is neither too complex nor too simple, aiming for better generalization on unseen data. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.